On the course landing page, we stated that calculus would be used in this course. Those of you who have had calculus may be wondering when that will happen. And those of you who have not had calculus may be worried about when that will happen. Well, here's some news for everyone. It's already happened. We've been using calculus already, even if you didn't realize it. Let's talk a little bit about where and how calculus is showing up in our work. Let's start, as always, with our fundamental principle, Newton's second law, in the form for predicting the motion future. Recall that when we have to use the computer to apply this principle, we start from an initial condition and predict for a small time delta t into the future, and do it over and over again. All these small predictions accumulate and, thereby, taken as a whole, allow us to make predictions over a substantially long period of time. Let's say a little bit more about this accumulation process. With each pass through the loop, a new final velocity is predicted by adding to the initial velocity a change in velocity. So for the very first pass through the loop, the first final velocity we predict is obtained by adding to the first initial velocity, which we will call v0, the first change in velocity. Recall that v0 is the one we specify at the very start. The velocity at the starting time we'll call t0 before we enter the loop. Note that the time t0 is equal to 0 in this code, but need not be. It just needs to be whatever time we started our clock at when we started our observation. Now the second time through the loop, we predict a second final velocity by adding a new change in velocity to a new initial velocity. Notice this new initial velocity is just the final velocity we predicted from the previous pass through the loop. So we could also write the second pass through the loop like this in terms of v0 and the sum of all velocity changes up to that point in time. Now we can do a similar thing for the third time through the loop, again writing the new final velocity in terms of v0 and the sum of all velocity changes up to this point in time. On the final pass through the loop, we predict the final velocity, which is the velocity at the final time t sub f, and is equal to the sum of all the velocity changes added to the initial velocity v0. Let's emphasize here that the way we calculate each velocity change is by using Newton's second law each time we pass through the loop. Notice that the velocity changes can differ from one another because the net force can change in time. Now, if the time step, delta t, is sufficiently small, then, in calculus terms, this sum of velocity changes is a very good approximation to the definite integral of the vector f net divided by the mass m multiplied by the differential dt, integrated from the initial time to the final time. So the upshot here is that when we have been using the computer to predict the velocity as part of predicting the motion future, we have been doing calculus in the form of integrating Newton's second law. In fact, when we cycle through our while loop, we are doing not just one, but two integrals, where the second integral is connected with our prediction of the object's position. In other words, we can show using the same thinking we just applied to predicting the velocity that when we predict the object's final position, we do this by adding to the initial position before the loop the definite integral of the velocity times dt integrated from the initial time to the final time. So now that we all know we've already been doing calculus with the help of a computer, some of you who have had calculus before may still want to know how to do these integrals the way that is typically taught in most introductory math courses, using methods to write down, with pencil and paper, solutions to integrals in what are called analytic or closed forms. We will show an example or two like this later. However, for many motion problems, analytic methods become quite difficult or even impossible. For example, it can be shown the general motion of only three objects interacting gravitationally cannot be solved analytically, no matter how many math courses you take. However, This problem can be solved numerically, that is, with the help of a computer. So although we haven't discussed gravitation yet, we will soon, and once we do, then most anyone in this course will be able to use the step-by-step iterative methods we've already learned to predict in a general way the motion of three gravitationally interacting objects. The bottom line here is that we now see that we will need to use, and we have been using, calculus to do motion prediction. We have been emphasizing the step-by-step iterative methods for doing the integration of Newton's second law because these methods provide us with the powerful techniques we need for tackling real-world motion problems. In closing, we emphasize that in using the computer to help us do the calculus we need, the computer is merely carrying out the repetitive work that is necessary to make these step-by-step methods practical. The computer is not doing the thinking. It's up to us to tell the computer which steps are the correct ones that are needed in order to apply our fundamental principles to understand and to predict the motion we're studying.